Thanks for the introduction. So my goal is to provide a value of local speed of sound here in a color map to aid a quantitative diagnosis, for example, of liver disease in pulse echo ultrasound. And the principle behind this technique, computed ultrasound tomography in echo mode or CUTE, is shortly summarized here. So the acoustic round trip time T of an echo that is generated at the position xz in the tissue is given by a path integral of the local slowness inside the tissue along the transmit and the receive propagation path. And this can be written as a sum of a time t0, which is given by a priori guess of sigma 0, plus the path integrals along the deviation of sigma from this a priori guess. Now the difference tau between t and t0 changes according to the changing path integral along the transmission path when changing the transmit beam steering angle. And this difference, delta tau, can be measured in the reconstructed RF mode image using phase correlation techniques. Oops. Sorry. So by measuring this delta tau spatially resolved, one can reconstruct the delta sigma using a frequency domain real-time capable reconstruction algorithm. And to make a robust result, instead of using just 2 transmission angles, typically it works best using 7 transmission angles, ranging, for example, from -30 to 30 degrees. And phantom studies show that this technique allows us to see the speed of sound contrast of lesions inside the tissue that are otherwise unsuspicious on normal B-mode ultrasound. We also were able, clinically or in humans, to differentiate the different speed of sound of different tissue layers, for example, here in the neck. And this after correcting artifacts that were associated with the rotating point spread function of the RF mode image when changing the transmit angle. Now, contrast is a nice thing, but optimally, we would like to have a quantitative value of speed of sound in addition to contrast to be able to do a quantitative diagnosis or staging of disease. And so this technique should then be operator independent as well as interpatient independent. So we really want to measure the real speed of sound value. Unfortunately, it turned out that this is very difficult in experiments. So in this phantom study, using a homogeneous phantom, the reconstructed speed of sound depth profile strongly depends on the initial guess, C0, of the speed of sound. And in layered phantoms, such as here, the speed of sound measured in a deeper layer depends on the thickness of the layer on top. So this would mean that the speed of sound that is measured in the liver would depend on the thickness of the fat layer, which is not good, of course. And also, there was a decrease of contrast in layered phantoms towards the lateral edges of the image. So, of course, such a technique is not suited for quantitative imaging. So, during the past year, we focused on further improving the technique to achieve quantitative imaging. And the question was, what was the problem in the previous implementation? So, it turned out that the problem was the transmission shadows caused by the limited transducer aperture. So, when you transmit ultrasound at a certain angle, there is always a region that does not receive ultrasound power, so you can't detect any echoes from there, and you can't measure the delta sigma in those regions. In simulations of homogeneous phantoms, assuming that we don't have this limitation, we could show that it should be possible to accurately reconstruct the speed of sound distribution. But as soon as we delete the data in those transmission shadows, we reproduce the experimental results. The same for a layered phantom. Assuming that there's no limitation in the aperture, you can reconstruct the different speeds of sound of the different layers. But when we assume the missing data, we can again reproduce the experimental results. So the problem of the previous implementation of Qt was the frequency domain reconstruction algorithm that is not capable of taking into account the regions of missing data. And for that reason, we turned to a space domain formulation. Now this looks a bit complicated, but the take-home message of that slide is that we can write the forward problem in Qt in a space domain as a matrix multiplication. And this is the matrix. Here you have all the delta sigma, and each line in this matrix contains the integration weights of one path integral. So for example, for this pixel here, only 3 weights are different from 0, corresponding to the 3 pixels in the image along the path, propagation path. And for pixels located in the transmission shadow, all elements are 0. So this matrix is inherently sparse. And this line is the forward problem for the local echo phase shift using 2 transmission angles. So in going all through the mathematical formulation, the most important thing is that we do an inversion of this forward problem for all transmission angles simultaneously, and we use a regularization of the spatial derivative of the reconstructed delta sigma. And this is in contrast to the frequency domain approach, where we used regularization of the average squared delta sigma. So now this reconstruction is still real-time capable because we can make use of the sparsity of the forward problem. So if formulated using sparse matrices, and if the matrix coefficients of the inverse are pre-calculated and then reused for each image reconstruction. So now we make a test of this algorithm, first in simulations. We can show that the reconstructed speed of sound does not depend on the choice of the initial guess C0, even though the depth profile is slightly inaccurate. Same in phantom studies, we see that independent of the choice of C0, we obtain the same depth profile within the noise. In layered phantoms, the simulation suggests that the speed of sound of this layer does not depend on the thickness of the upper layer, and the same in experiments. It doesn't look that nice, but you see that the layers are reconstructed in a much better way than using the frequency domain approach. So, by explicitly incorporating the missing data in the formulation of the forward problem, accurate reconstruction of the speed of sound can be obtained. In addition, this new algorithm allows us to take into account other regions of missing data, such as a cyst, which does not contain echoes. And this is simulation where you have a lower speed of sound region inside the background. And if we now assume that there is no data available in this region, normally this would produce huge artifacts. But when we incorporate the absence of data in the reconstruction formulation, we can get the same image as here. Unfortunately, the experiments didn't turn out well yet, but this is just from a homogeneous phantom where artificially introduced a data hole. Then you get again artifacts, and then by incorporating this data hole in the reconstruction process, you can again get back the initial image. So this is very promising to be able to do speed of sound imaging inside blood vessels or cysts or any other hypoechoic regions. Now to investigate the reproducibility of quantitative imaging, I performed a longitudinal study of liver imaging in myself over a course of 1 month and over different scanning locations. So the hope was that, the speed of sound doesn't depend on the scanning location, so on the anatomy on one hand. And on the other hand, I was hoping that I could see some change over 1 month due to some biological rhythm. And this is a typical movie of our real-time implementation on the Verasonic system. And it currently runs at a frame rate between 1 and 2 frames per second, depending on the resolution of the image. And on the left, On the left side, you see the B-mode ultrasound, so you see the fat layer, the muscle layer, again a fat layer, and then the liver tissue. On the right side, you see the speed of sound color map superposed to the B-mode ultrasound image. So you can see the consistent change of speed of sound between the fat layer and the liver. Fat is blue, liver is orange. And it correlates well with the anatomy of the liver. You can see the same for the muscle, which has a slightly higher speed of sound than the fat. Unfortunately, in this region here, the axial resolution of the speed of sound image is too low, so part of the blue from the fat layer radiates into the muscle. But you see that this result is very consistent when scanning over the body. And on the next slide, you see in this plot, you see the standard deviation, the average value and standard deviation of the speed of sound measured in different tissue regions. So here you see the liver, here you see the muscle, and here you see the subcutaneous fat layer. And you see that the speed of sound values are within the standard deviation reproducible. And each group here corresponds to 4 different scanning locations on my belly. And you see that also, independent of the scanning location, the speed of sound values are the same within the standard deviation. You also see that it's possible to distinguish different tissues based on the speed of sound, especially, of course, the fat layer has a much lower speed of sound. And the standard deviation here is 10 meters per second, and this is actually already quite good to determine the fat content in the liver, for example. So the liver speed of sound changes drastically depending on the fat content. And this could help diagnosing the amount of fat in the liver and thus aid diagnosis of liver fibrosis and using elastography, because the fat also influences elasticity. So currently it's difficult to quantitatively determine the fibrosis, but this could help to get a more accurate diagnosis in fatty patients. So the conclusions. The space domain formulation of QUTE is a key step towards quantitative speed of sound imaging. The space domain formulation allows reconstruction of speed of sound in presence of anechoic tissue, which is very important. And we already obtained reproducible speed of sound values in the liver in volunteers with a standard deviation of plus minus 10 meters per second. Hopefully, we can achieve better contrast resolution in the future. And also, what I didn't tell, there are still some model flaws. So one of them I just encountered 2 weeks ago that made it possible to get quantitative value. And this is actually not yet implemented in the real-time implementation. So there was still a slight dependence on the speed of sound. But now this is solved, and we hope that it will get better. Thanks for your attention.